Web3 has historically been limited by its own interfaces. Every transaction, smart contract deployment, and cross-chain bridge depends on a human user to manually click, approve, and sign. It's a system defined by manual confirmations and human coordination. This creates a structural bottleneck. When a digital system requires a human-centric interface to function, it introduces a level of latency that limits the speed of complex workflows. As workflows move towards sub-second execution, traditional platforms struggle to keep pace. The machine economy addresses this by giving AI agents direct spending authority. These agents operate with private keys, allowing them to autonomously negotiate contracts, manage daily operational budgets, and actively rebalance treasuries. Most corporate workflows are currently managed through emails, meetings, and manual database reconciliations. Autonomous machines consolidate these layers. They operate across multiple blockchains simultaneously, executing decisions at the speed of an API call. By removing the friction of human oversight from the execution loop, the next generation of digital infrastructure moves entirely out of sight. It captures value by making the underlying financial logic invisible to the end user. There is a specific engineering risk in giving standard large language models access to decentralized capital. These models are inherently stateless and probabilistic. They are designed to predict the next token in a sequence, which makes them unpredictable when they are required to function as rigid financial actors. This results in the memento man problem. A stateless AI resets after every API call. It has no internal mechanism to preserve its operational history or strategic context from one query to the next. To manage autonomous capital safely, developers must build a deterministic control plane. This new layer serves as the bridge between fluid language models and the absolute certainty of cryptographic ledgers. The Denarii DFi Orchestrator is this architectural bridge. It provides the structure necessary to coordinate specialized agents, preserve their memory, and translate high-level intent into a secure, autonomous business reality. For autonomous value flows to be effective, the base infrastructure must be free of network congestion and high transaction costs. If an agent has to wait for human-scale consensus, the advantage of automation is lost. This trinity of DLT integrates three ledger architectures. Algorand provides mathematical finality for standard assets. The XRP Ledger handles high-speed value transfer and liquidity routing. Hedera Hashgraph generates the high-throughput, sub-second audit trails needed to verify every machine decision. By utilizing these three chains, the orchestrator allows AI agents to bypass fragmented liquidity and high network fees. This multi-chain abstraction provides the only architecture capable of supporting machine speed execution without being restricted by the limitations of a single blockchain. As the cost to deploy AI automation drops, it creates what economists call the measurability gap. This occurs when the speed of machine execution outpaces the biological ability of humans to verify the results. The danger of this gap is the hollow economy, a system where massive volumes of unverified transactions are processed, increasing the risk of systemic failures. Without intermediate verification, an autonomous system's error rate compounds. If a single agent makes a logic error at step 3 of a 5-step task, it continues on a flawed foundation, leading to a total system failure at step 5. The orchestrator prevents this by injecting an independent QA agent into the loop. It audits the primary agent's work at every checkpoint, verifying code before moving to the next task. This check and balance mathematically resets error probability, securing complex deployments. To maintain stability, the orchestrator uses a heartbeat check-in system. This is a recurring loop that forces every agent to reread its overarching organizational goals before it executes any new command. Strategic context is preserved through projects, areas, resources, and archives, giving the AI persistent history without exceeding its token limits. Inside the Paperclip AI Orchestrator, these mechanisms organize specialized models into a structured corporate hierarchy. CEO, engineer, and treasury agents all operate from the same stateful context, allowing them to function as a unified organization. This system is protected by a strict entry requirement. To access the stateful orchestration dashboard, operators must hold 2% of the total DFI token supply. ensuring they have a direct stake in the network's performance. By enforcing this stateful memory loop and token-gated access, the orchestrator transforms a group of stateless models into a reliable, continuously operating company. No autonomous agent is permitted to touch live capital with empirical validation. This is a core safety directive of the architecture. Validation occurs in the agent sim game, a gamified sandbox environment where operators can test agent logic against extreme conditions before deploying to a live ledger. The simulation visualizes the machine economy as a holographic physics graph. Operators can monitor capital streams flowing between agent nodes to ensure the system is in a healthy baseline state. To test resilience, an integrated AI dungeon master is programmed to actively break the system. An operator might inject a synthetic crisis, like a flash loan liquidity drain, to see how the swarm reacts to a sudden loss of capital. The results are immediate. The dashboard shows plummeting macro metrics as the treasury drains and the trust index falls into the red zone. This requires a real-time response. The operator must diagnose the failure vector while the system is under simulated stress. The operator uses the orchestrator's AI mitigation planner to generate and deploy a technical isolation script. Once active, the capital streams recover. Simulated metrics turn green and return to baseline levels, proving the fix was successful. Successfully managing these crises gives the specific agent configuration an on-chain reputation score, verifying its readiness for live deployment. This sandbox method ensures that only agent swarms with a mathematically verified trust index are permitted to manage real-world institutional capital. After an agent is validated in the sandbox, it transitions to live execution on the mainnet, where real multi-chain assets are stored. These assets are managed within the vault, an automated cryptographic core designed to store and settle capital through machine logic. It uses trusted execution environments and quantum security to isolate operations at the hardware level, preventing unauthorized key extraction while agents manage transactions. For major state changes, the system requires biometric decentralized identity scanners. This adds a layer of human-in-the-loop authorization that is cryptographically verified before any high-value transfers occur. This combination of physical enclaves and cryptographic shields ensures that when a swarm makes an economic decision, the resulting execution is tamper-proof. The architecture is now complete. It begins with base cryptographic ledgers and stateful cognitive agents, which are validated by synthetic shocks and secured by hardware enclaves. In this model, the primary technical value has migrated from the user interface to the coordination layer. The orchestrator converts natural language intent into institutional-grade action across multiple chains. It eliminates human latency by allowing machines to coordinate and settle value at the speed of the network. The infrastructure for a machine economy is operational. It is currently managing capital and executing cross-chain workflows with absolute machine precision.